All right, so let's get a little bit more practice here with spherical coordinates. We talked about converting between spherical coordinates and Cartesian coordinates, and now let's talk about two special types of things. So we talked about cylindrical boxes when we talked about cylindrical coordinates. Now let's talk about spherical boxes. That is, what are nice equations that are best represented in terms of spherical coordinates? And that's going to be the case. We're going to want to convert when we have inequalities that kind of look like this, where we've specified what, like, constants as your bounds for phi, for theta, and for rho. So when we say rho is between 2 and 3, remember rho is the radial distance. And so that's telling us that we have a sphere of radius 3, and inside we have a sphere of radius 2 that's not allowed. So it's a hollowed out sphere that has the outer radius 3, the inner radius is 2. Then by specifying that phi goes between pi over 2 and pi, what that's doing is it's saying, so phi, remember, is the angle from the top, so that's telling us we want to start at pi over 2 and we want to go all the way down to pi at the bottom. And so this is giving us basically a bowl shape where the outer radius is 3 and the inner radius is 2. And that's a region that we can specify using spherical coordinates. Similarly, here we have phi goes from 0 to pi over 3. So from 0 to pi over 3 would be here, and rho is less than or equal to 2. And so what we get there is we get a cone. The angle of this cone is pi over 3, but then it has a spherical top, so it's kind of like an ice cream cone, where the radius here is 2, and the radius to every point there is 2. And so that's talking about dealing with rho being in a range, and that's talking about phi being in a range. And so the only other thing we have to talk about is theta being in a range. And remember, what theta does is it chops off, it's talking about the angle around in the x-axis. So a spherical box is going to be something where you sweep out some angle in the theta direction, you sweep out some angle in the phi direction, so maybe from here down to here. Yep. What's happening here? We have to sweep this out. And we also have to sweep out some direction in the rho direction. So then this could be sliced and have a center hole in it. So a spherical box corresponds to something where rho is between rho naught and rho 1, theta is between theta naught and theta 1, and phi is between phi naught and phi 1. And so that's going to give this piece of a sphere where you've got some angles that are defining this on the sides, you've got some angles defining it around wise, and you've got some distances from the origin. So it's just like an annulus corresponds to taking a bite, the center circle out of a circle. We've got this nested spheres, or this hollowed out sphere that you get when you're dealing with spherical boxes. All right, now let's do some converting to spherical coordinates. And so in this setup, what we'd like to do is we'd like to use our techniques to see what we get. So if we wanted to convert these things to spherical coordinates, we could actually plug in our x, y, and z and then solve. So z is equal to rho cosine of phi, and then x squared plus y squared, well, we already figured out that that's the r, and r was equal to rho sine of phi. So x squared plus y squared is rho squared sine squared phi. And so if we're writing this down in terms of rho as a function of phi and theta, we get rho is equal to cosine of phi divided by sine squared phi. That would be a way to write down that equation. On the other hand, here we have something a little bit more complicated. We have rho cosine of phi is equal to rho sine of phi cosine of theta squared minus rho sine of phi sine of theta squared. And so if we factor out a rho sine of phi from both of those equations and divide, we get cosine of phi divided by sine of phi is equal to cosine squared theta minus sine squared theta. And so that may be the best way to represent this. There's probably some better way to do that. So maybe we'll go to Mathematica, try to simplify it. If we have, so what do we want to do? We wanted to replace all, we had something that looked like, we wanted to replace all the x's. So let's look at z minus x squared minus y squared. Let's look at that one first. So that was the first thing that we found out. This was equal to 0, so if you then solved, you either get rho is equal to 0 or you get this other equation. And if we did z minus x squared plus y squared, then we get this expression. And so what we're getting is we're getting an expression that says this equation equals 0. And so if we want to solve for phi, solve this for, let's solve it for rho. Then we get that this is the equation, rho is equal to cotangent of phi, cosecant of phi, secant of 2 theta. And so that means we could plot it. So we could do a spherical plot of this thing. Oops, where this is phi and this is theta. Whoa! Craziness. Let's see what happens if I... So I've already interchanged phi and theta. I wonder why it's not working. Probably it has to do with the number of plot points that I'm using. So let's see what happens if I did plot points goes to 100. And let's see how nice that looks. We're getting there. Maybe more points would give us something even better. Where are these things not defined? They're defined in all those places. I'm looking from above and it looks like it's just having trouble with what these values are. So what if I just did phi goes from 0 to pi over 2 and theta goes from 0 to pi over 4? Maybe that would give us a nicer equation. Just restricting these, the domains is going to allow it. Oh, okay, so now we're starting to get what we need. We're starting to get to see this hyperboloid. So it had to do with what the domain of the function is each of the times. All right, so can I expand this to pi over 2, or does that still break it? Yeah, that still breaks it, but maybe I can go from negative pi over 4 to pi over 4. I'm just trying to get a little bit more of this function. And again, this is starting, like you can see the function there, but it doesn't, oh, negative pi over 2. So I want a negative pi over 4, and what if we do the full phi? Let's see if we can get this function working right. So by specifying the values of phi, oh, this is starting to look really, really good. So now we'll do plot range is 10, and then maybe we'll actually get to see what we hope to see here, which was the curve, this hyperboloid of one sheet. Look at that. There it is. It's coming right out. So here we've gotten Mathematica to use spherical coordinates to plot this z equals x squared minus y squared curve. All right, let's head back over, get a couple more questions done. So give the solid that's inside x squared plus y squared plus z squared equals 4, above the xy plane, and below z equals square root of x squared plus y squared. So we're looking at this, we see a sphere. We see something we want to be above the xy plane, and we want to be below some other function. So z equals square root of x squared plus y squared, so that's our cone. Okay, so now, so what we're doing is we're looking for a region that's inside the sphere, below the cone, but above the plane. So this is kind of like the reverse of an ice cream cone. It's like what's underneath the ice cream cone when you have that. And so we'd like to take this type of region is one of the examples of those spherical boxes, and let's write down what it is in terms of rho, or in terms of sigma, theta, and in terms of phi. All right, first thing, let's look at maybe phi first. All right, so this equation looks a lot like this equation for tangent of phi. I mean, we're looking at this, we're seeing this as a cone, and because it's a cone with a certain angle where you have a relationship between how far you move over in r and how far you move up in z, and you're seeing that that's the same. So this is the equation z is equal to r. In other words, what we have here is that tangent of phi is equal to 1, or that this angle, phi, is pi over 4. So what we get is we get the angle where phi starts at pi over 4 and then continues down to the plane, which is phi is equal to pi over 2. So phi goes from pi over 4 to pi over 2. Theta here, because we're dealing with the whole circle, theta goes from 0 to 2 pi. And then the last part is rho, and rho we had the solid inside, x squared plus y squared equals 4. And since it's x squared plus y squared plus z squared is less than or equal to 4, no, it doesn't want me to remove that, then phi is going to be between, no, sorry, rho is going to be between 0 and 2, because rho squared is up to 4. So these are going to be the bounds on rho, theta, and phi. So that's one way to represent this region as a spherical box. The last thing that we might have to do is, if we're given an equation where given a triple integral that's in terms of x, y, and z, and your goal is to write it in spherical coordinates, well, as always, we're going to draw a picture. So what do we see? X goes from 0 to 1, right? So let's first draw the xy plane. X goes from 0 to 1. Y goes from 0 to 1 minus x squared. So that's a quarter circle. So we're in the two-dimensional projection is that. And z, above this, z is between the cone. Z is equal to x squared plus y squared. That's just like what we had here. And z is less than or equal to a sphere. So if z is equal to square root of 2 minus x squared minus y squared, then that is that x squared plus y squared plus z squared is equal to 2. And so that's giving us the radius here, that rho is less than or equal to root 2. So that's what that top part of the function is. And so if we want to write this down in spherical coordinates, what we get is, so this z, oops, not z, if we're looking at this, rho goes from 0 to 2. We are looking at all of the points that are above this cone, which is telling us that we want phi to start off at 0 and come down to this angle here, which we calculated before was pi over 4. So phi goes from 0 to pi over 4. And now theta is a little bit different because it's not the full circle, it's only starting at 0 and it's going up to the y-axis, right? So theta goes up to the y-axis, which is pi over 2. So theta goes from 0 to pi over 2. And then if we're integrating, remember this is f of rho, phi, rho, theta, and phi. But don't forget your extra term that we have to put in here, rho squared sine phi d rho d phi d theta. All right, and so that would be how you convert from this integral here that had to be over some x, y, and z bounds into a spherical integral. So that's about it for this topic and for the course. Thanks so much for following along. All the best. Take care. Bye.